Hi, in this lecture video, I'll be going over energy diagrams, how to read them, and how to construct energy diagram as well that will correspond to the mechanism of a reaction. So here in organic chemistry, we'll be learning many reactions that are considered to be multi-steps, meaning that the reactants, as it getting converted to the product, it does not happen in just simply one step, but it produces various intermediates and transition state in the middle between the reactant and the product. And the intermediate are basically the short-lived species that they form during a multi-step reaction, and they're unstable compared to the product and therefore cannot be isolated. And these are basically the values in the energy diagram. So here below is an example of the energy diagram of a reaction. So this point right here, so these are the reactant, the starting point of the reactant, and here are the products. So all the value in between the reactant and the product, these are known as the intermediate. So this intermediate right here are stable compared to the transition state. However, they are not as stable compared to the product, and therefore they cannot be isolated. And the transition state are basically the structures that show the interaction between reactants or between intermediates. And in the transition state, they will be showing the bond breaking and the bond forming, and also charges that are forming and disappearing as well, as the reactants or as the intermediate are interacting with each other to produce bond and break bond. And these are basically the peak in the energy diagram, and these are the peak right here. So in this case, we have 1 peak, 2 peak, 3 peaks, and each of these peaks right here correspond to a transition state. And the step with the highest activation energy, that would then be the rate determinant step. So here in the course of this reaction right here, based on this energy diagram, this is a 3-step reaction. How do we know this is a 3-step reaction? Then the answer, because there are 3 activation energy that we're observing right here. So each of this activation energy refers to 1 step. So we can think of the number of activation energy as a step, or for each of the step, it will have a transition state. So in this case right here, there are 3 transition states. So this tells us this is 3-step reaction. So the first step is as follows. The reactants interact with each other. And as the reactants are interacting with each other, they come colliding together and bond breaking and bond forming. And as we can see, that is the step that is quite high in energy. So again, the transition state is showing, in this case right here, this transition state will be showing how the reactants are interacting with each other. And after the bond breaking and bond forming happen already, we now drop down here to an intermediate. And then this intermediate right here will be interacting with each other again, producing another transition state. And then once all of the bonds have been forming and breaking, we're dropping down to another intermediate again. And then the intermediate here, so we'll be going to the 3rd step to get interacting with each other, and then producing another transition state right here. And this will be the transition state number 3, and finally leading to the formation of the product. So here in this case, this will be a 3-step reaction. So we can think going from a reactant, going from one hill or one valley to another valley, that will then be 1 step. So go from reactant to this valley, this is 1 step. Going from this valley to this valley, this is another step. And going from the valley to the product, another step right here. And again, the step with the highest activation energy is the rate determinant step. The rate determinant step is the step that has the biggest effects on the reaction rate overall. So it is this step right here that dictates how fast or slow the reaction will be. So here in this case, based on the energy diagram that we're seeing, the step number 1 would then be the rate determinant step, because this is the step with the highest energy. So the reaction can only proceed as fast as this rate determinant step right here. And now let's put all of this together right here and learn how to construct the potential energy diagram. So again, an energy diagram describes both the kinetic and the thermodynamic of a reaction, and it correlates to the reaction mechanism. And so we'll be taking a look at the different number of pumps depending on the number of steps that are being involved. So let's now learn how to construct the simplest types of reaction energy diagram first. And in this case, this is the one-step reaction. So the simplest types of reaction energy diagram. So here is an example of a generic one-step reaction right here, where we have A and B right now bonding together and then reacting with C. And in the course of this reaction right here, then the bond between A and B is broken, and now the bond between C, B, and C are being produced. So this is a one-step reaction right here. And a one-step reaction can be exothermic or endothermic, depending on what it is. So let's now consider the first scenario. Let's say we have a one-step exothermic reaction. So how would we construct an energy diagram? So here in this case right here, on this axis, we can be putting various variables that we are interested in. We can be putting energy, potential energy, or also enthalpy. And in this case, since we are discussing endothermic and exothermic reaction, our emphasis would then be on the enthalpy. And that is what we are plotting right here. Now, so in this reaction right here, so starting from the reactants here, and on the product, on this scale in enthalpy, then we have to be putting the product of lower enthalpy than a reactant, because this is an exothermic reaction, meaning that the products actually have lower enthalpy compared to the reactant. So therefore, this reaction here would be releasing heat into the surrounding. And so again, the product, it is crucial that we have to put the product having lower enthalpy compared to the reactant. And we would then be drawing this line right here that would then represent the heel and leading to this transition state right here and finally go into this product. So in the course of this reaction right here, there's a no intermediate. So for a one-step reaction, there's a no intermediate. Please be aware of that. Now, there's one transition state, and in the transition state, this is when this molecule and this substance right here will be interacting with each other. And here in this case right here, we'll be seeing in the transition state that the bond between A and B are beginning to break. So this is why that we dash in this bond. And the bond between B and C are beginning to form. And this is why we also dash in this bond as well. So this means that this bond right here is being broken. So bond breaking. And this line is showing bond forming. And this will then be the structure of the transition state. So again, on the transition state, the reactants are colliding, and bonds are breaking and forming, and charges are also appearing and disappearing as well. Now, in this energy diagram right here, there's a few more things that we can learn from it. So here in this case right here, we would then see that this is the transition state, and of course, this would then be the activation energy that is needed to get from reactant into this transition state. And the reactant in this case right here are closer to energy in transition to the transition state compared to the energy between the product to the transition state, right? Because this is the energy of the reactant, and this would then be the product. So we can see that the reactant and the transition state are closer in energy. And now we also observe the following as well. So in this case right here, going from here to here, the distance from the reactant to the product from here to here, this is closer compared to the transition state to the product. So basically, this is also showing that they're closer in structure. When the reactant is closer to the transition state, that also means that it's closer in structure as well. And that brings us to this Hammond postulate right here that state a few things as follows. First, related species that are similar in energy are also similar in structure. So if they're similar in energy, they're also similar in structure. And therefore, for an endothermic reaction, the transition state resembles the product. versus for an exothermic reaction, the transient state resemble the reactant or similar to the reactant. And that is what we observe in here in this case right here, that this is an exothermic reaction. So the energy, the reactants have better resemblance to the transient state compared to the product, because they're closer in structure and also closer in energy as well. So for this reaction, the transient state resembles the structure of the reactant more than the product. And overall, this reaction right here would have a negative delta H of the reaction. So if we were to be taking the delta H of the product minus the delta H of the reactant minus the H of the reactant, then in this case right here, we'll be having a negative delta H of the reaction. And that's what this reaction right here would then be exothermic. Now this reaction right here would also be spontaneous as well, because the product have lower energy compared to the reactant. And now let's go over what would be the difference in case we have an endothermic reaction instead. So the fact that this is an endothermic reaction should tell us that we have to continue applying heat in order to make this reaction go. So here in this case right here, this is because the reactant have lower enthalpy compared to, or have lower enthalpy compared to the product. So here in this case right here, the product have a better resemblance to the transient state. So the energy gap here would then be smaller. And that also means that the structures of the transient state have better resemblance to the structure of the product. And this would then be the activation energy. So again, we always need to have some sort of activation energy. Any step would need some sort of activation energy, because as the reactants are coming together, whether the reaction is spontaneous or endothermic or exothermic, when the reactant come and colliding with each other, that is a step that would be high in energy. So here's again, the bond between B and C are beginning to break, and the bond between A and B are breaking, and the bond between B and C are forming, leading to this product over here. So in this case right here, we would then see that overall the delta H of this reaction, we have to take the H of the product minus the reactant. In this case, this would then be a positive delta H of the reaction. So therefore, this reaction right here is endothermic, requiring heat. And this also means that this reaction right here will then be non-spontaneous. We have to continuously apply heat energy in order to make this reaction going forward. And now, let's learn how to construct the potential energy diagram for a reaction, a real reaction. So in this case right here, it is the reaction between this double bond and HCl to produce this product. So this is a hydrohalogenation reaction, one of the reactions of alkene that we'll be discussing later. So here in this case right here, what will be the mechanism of this reaction, providing the product as follows. So we see the following. So here in the course of this reaction right here, then we can see that the double bond, the alkene, is an electron-rich substance. So therefore, it can come in and acting as a base and come in and grabbing this proton right here and picking up this proton, because this proton right here will then be acidic. So come in and grab this proton, and as this happens, the bond between the H and the Cl has to be broken in order to restore the bonding for the hydrogen. And so basically, when we follow through with this step right here, we'll be having the following. Now, In this case right here, we are trying to draw the potential energy for the reaction that produced this product right here. And please, later on, we'll learn that this is actually not the major product, but this is only a minor product right here. Okay, so please keep that in mind. So initially, we'll be producing this intermediate. And this reaction here can again proceed in a different direction where we can also produce different product. And the other product is basically when the chlorine will be added to this carbon over here rather than the other carbon. So this will be the major product, as we'll learn later. But for now, we'll have to explain the formation of this minor product over here. So these are the intermediate. And once we have produced this intermediate already, the chloride has a rich in electron, so it can come back in and attack this carbocation and leading to the formation of the product. So this is quite a simple reaction right here. But now, let's now consider the transition state. So on the very first step, we can see that the double bond is acting as a base to come in and grab this proton right here. So in the end, we can see that the bond between this carbon and this hydrogen is beginning to form. And the bond between this hydrogen and this chlorine is beginning to break. So let's draw that transition state. So the transition state number one will basically be involving. So first, the double bond is beginning to break apart. And now the bond between this carbon and this hydrogen is beginning to produce. And the bond between the hydrogen and the chlorine are also beginning to break as well. So this will then be the transition state. And now, in the course of this reaction, the double bond initially donates an electron to pick up this proton. So it will then go from being neutral to being positive, right? But in the transition state, it only be partially positive because this is beginning to happen. So it hasn't happened yet, but it's still in process of happening. And the electron is then donated to this chlorine. So in the end, we can see that this chlorine right here is beginning to become partially negative. So that's how the charge are appearing and disappearing in this transition state. So this will be the transition state of this step. And now once we have produced this intermediate already, then we will now be seeing that these two intermediate are interacting in the next step. So this is a two-step reaction. So the first step is to produce this intermediate. And now this intermediate will interact with each other to finally produce the product. So in the structure of this transition state, we can then see that the bond between the chlorine and this carbon is beginning to form. So therefore, the transition state structure of this will look as follows. And now we will then see that right here, the chlorine is fully negative and it beginning to donate electron away. So now it only remains to become partially negative. And this carbon, as it beginning to accept electron, it will go from fully positive to now partially positive. So that will be the structure of the transition state when this intermediate coming in and interacting with each other. And this symbol right here represent the transition state. So this will be the transition state number 2, whereas this would then be number 1. So this is a two-step reaction. So this is the mechanism of the reaction with the intermediate and the transition state being drawn out. And now let's apply how we can construct that. So first, in the course of this reaction right here, and let's say assuming we are given this information right here, this reaction right here is exothermic. So when we know this is exothermic reaction, when we plot this, the product needs to be placed lower compared to the reactant. So let's say here we have the reactant. And this is two-step reaction. So there has to be an intermediate in between. So this will be one intermediate right here. And then this would then be the product. So first, place those in first. And of course, the reactants have to have lower energy compared to the intermediate, because the intermediate a lot of time are really unstable. And now we would be able to construct the following. So first we need to draw up, and it has to go to a transition state, right? So we're gonna draw this line up real high, and finally dropping down here to this transition state to produce this intermediate right here. And from this intermediate, we can now draw another transition state where the intermediate are beginning to interact with each other. So here in this case, let's go ahead and assume that this transition state number 2 right here have lower energy compared to the first transition state. And it makes sense, because what happened is that in this case right here, it have less molecule, less interaction right here. So there's less thing that happening on the transition state number 2. So therefore we have lower energy. So let's go ahead and tentatively put it somewhere over here. And finally, reach into the product. So that's how we can construct this. And so in this case right here, this would be the first activation energy, so the EA1. And this would then be the activation energy for the second step, EA2. So this E would be the intermediate. And now let's draw the structure in. So the reactant would have the following structure. So we're going to put them in. And now when we get to this point right here, this is the transition state when these two reactants begin to interact with each other. And earlier we saw what that structure would look like. So which is the structure from above. So therefore we're going to draw this structure. And that will be the transition state structure number 1. And now, once the bond had broken already and forming already, we'll now be producing the intermediate. And the structure of the intermediate, as we have seen previously already, this is when we have a carbocation right here and the chloride. And now the chloride, these two intermediate will begin to interact with each other and producing the transition state number 2, as what we have drew up here. And this is the transition state number 2. And finally leading to the formation of the product. And the structure of the product will be as follows. And overall, we've been told earlier that this reaction right here is exothermic. So basically, if we were to be plotting the energy differences between the reactant and the product, so in this case right here, this would be a negative delta H of the reaction. So this is exothermic. And this would also be a spontaneous reaction as well, because the product have a lower energy compared to the reactant. So overall, this is how we would be able to construct the potential energy diagram of a reaction. And again, this is a two-step reaction. But has it been one-step reaction, it would be easier. And in this reaction, the first step, this step right here, would then be the rate determinant step. Because this is the step that have the higher activation energy.